Hello, this video is going to be about second order plus dead time temperature systems and how to calculate the symbolic formulas for the controller gains. And to start out with, we're going to look at the plant. I have a plant transfer function and the controller transfer function. The plant transfer function has the open loop gain, and this is in degrees per percent output. This is a dead time. Theta P is assumed to be in minutes, and we have two time constants, which is why it's called a second order. The controller is the standard ISA PID, where there is the proportional term. This Kc times Ti is the integrator term, and the Kc times Td, which is the derivative time constant, is the derivative term. The formula for a closed loop transfer function is here. Again, you have the transfer function for the controller is multiplied by the transfer function for the plant, and then this term is down below. We add 1 to it. So this is the closed loop transfer function. But what we want for the closed loop transfer function is this. There's nothing we can do about the dead time. The dead time will still exist, but we want the two time constants to be set by us by setting these closed loop time constants. So to continue on, what we need to do is solve for the controller transfer function. And we do that, and this is the result here. So if I solve for G sub C, this is the result. And now I have the two desired transfer functions here. So what I need to do is substitute the desired transfer function in for this T of S in here and here. And then the next step is to substitute in for the plant transfer function. And I do that here. And the plant transfer function is using equation 1 from up here. So it's a bunch of substitutions so far. And now I get into some of the nitty gritty and why it's handy to have a symbolic math processor. I use the simplify instruction, and I know this doesn't look simplified, but this is the controller transfer function. And the problem that we have is we got to get rid of this e to the minus theta p because this is the dead time, and we're going to do that by using a Taylor's approximation. We're going to use the first three terms. So we got the 1 minus theta p, and this is the third term here. So this approximates this as long as the theta p is relatively small. So I make this substitution, and this term here gets replaced by this term here. Okay, then I simplify again, and I know this doesn't look like a controller gain, but it's actually a controller gain and a low pass filter. The controller gain part is here, and the low pass filter part is here. And so what I'm going to do is simplify this or separate them out. This is, again, the controller transfer function, and this is the low pass filter. And the problem with the low pass filter is when S is equal to 0, this is going to be a very small number. So what I'm going to do is multiply this by the low pass filter by this term by dividing the denominator. Dividing the denominator is the same as multiplying the numerator. And then because this is multiplied, the whole term is multiplied, I have to divide by this, this term in the controller gain. So now I have the low pass filter, and when S is equal to 0, the gain will be 1, which means when at low frequencies, the low pass filter will have no effect. And this is the closed loop or the controller gain or the controller transfer function. And I know that it doesn't look like much now, but we're going to do some magic. Again, this is why it's nice to have a symbolic processor. This is the controller. transfer function, and this is the ideal controller transfer function. And what we need to do is solve for this KC, uh, KC and the KC here, and the TI and the TD, or tau D, tau I. And basically what this is doing is it's solving for three equations and three unknowns. And the three equations are powers of S. And so what I'm first doing is I figure out the coefficient for each power of S, and then I solve. And what I get is the uh, controller gain is this term. This is the controller integrator's time constant, and this is the derivative time constant. So here I write them out just to look pretty. And also I write out the low pass filter time constant. The closed loop time constant can only be, it has to be greater than 0.707 of the dead time. And the reason why is because if not, then this term would be negative. Now, it's possible that I could really ignore this term and make the controller time constant smaller, but I didn't in this case. Now we're going to assume that I did a system identification. And in my system identification, I got a value of 2.5, 2, 1, and 20. This is the ambient temperature. This is the dead time, the two time constants. Again, this is plant, um, the plant gain. So I calculate out a closed loop time constant, and I assign some numbers. And these are the gains that I get, assuming that my system identification was correct. But I don't like to make that assumption. So what I like to do is kind of randomize things a little bit. And I'm going to randomize the actual plant parameters by using this R norm. And what it's going to do is it's going to have a standard deviation of 10%. So it's going to be able to change these variables by quite a bit. And typically my system identification is accurate within 5 or 2%. I don't have these very widely varying numbers, but you will see that the results are quite robust. Okay, so now this is my update time, and 1/60th of a minute is a second. I have the continuous time arrays for the transition and input coupling arrays. I have to convert those to the digital domain. If you have MATLAB, it will do this for you. MathCAD does not have that feature, so I have to do it myself. Now, this is my PID simulator, and each iteration is going to take a set point, and this is the state, and the state happens to be a temperature and a temperature rate. The control output, this is the delayed control output to simulate the dead time, and the error from the last time, and that's for the filtering. So what I'm looking for is the difference in the actual position, because or the actual temperature, because what I'm using is I minus PD. And I minus PD differs from a PID in that the proportional and derivative terms are in the feedback path, which means that they only act on changes in the feedback, not on the error. So I'm going to just skip around here a little bit. The integrator is working on the error, but the proportional and derivative terms are working on changes in the state. And I've got to remember this is a temperature and temperature rate, and I have a limit of 100 and 0 for my control output. This is updating the state, so I have the transition matrix. So this is the current temperature and temperature rate. This is the new temperature and temperature rate. This is the delayed control output for simulating the dead time, and I multiply that by the input coupling matrix. And this part simulates the fact that the system has an ambient temperature, and the ambient temperature will go down to 20 when you remove this control output. It won't go to 0. So you have to be able to simulate the ambient temperature. This is the low pass filter, and what it's doing is it is filtering out this noise. I've added a little bit of noise to the output, my measured values. So I can test out how robust this system is as far as responding to noise. This is the number of iterations or seconds for the dead time after things have been randomized. You see my coming back up here. My dead time is assumed to be longer than 1 minute, so that ends up being 68 seconds. Come down here. And this is for doing the delay of the control output. And what I'm simulating here is the temperature is going to be ambient to begin with. Then it's going to step up to 100%, and then it's going to step down to 50%, so you can see how the transitions work. And this is the PID, and this gets called for every iteration, as n goes from 0 to n. And you can see, well, I don't display what n is here. But in any case, this is the set point. This is the temperature and the temperature rate, the control output. This makes sure that my indexes don't go below 0 for computing the delay for the control output. And then this is the error from the time before. And then this is the next iteration. So this is the temperature response given my step jump. And you can see that this should be at 20, but because I randomized things, the steady state process variable in this case is 17, almost 18 degrees. If the temperature goes up 20, goes up 100 degrees, this should go up 50 percent because the gain is 2, but it doesn't need to go up quite so far because my gain is actually greater than 2 because of the variance or the errors in my system identification. So now if I hit the control F9, you can see that it's varying the parameters by quite a bit. And you can see that the response is very good, even with widely changing dead times and and uh, gains and time constants. So let's go back to the dead time, and let's see how this fares with a longer dead time. Now you can see this response is pretty quick because the closed loop time constant is small, and that's because the dead time is small. So let's go back up here to where the dead time is, and let's make this a 5. Oh, let's make this we'll make it 10. Now, this is actually very long. Whenever the dead time is that much longer than the longest dead time, it's going to be difficult to tune, at least to tune it manually. So we're going to go back to the plot. And you can see that the closed loop time constant has increased from 0.71 to 7.1 because I've increased the dead time by a factor of 10. But you can still see that it controls nicely. And let me just show some more. There it's a little bit low, and the reason why is because this gain is very, very small. It's not close to 2. There's a, what is it, about 25% variance there from the my assumed model. There it's much closer. And also notice that the response is much longer because the closed loop time constant is longer. So wrapping it up, let's go back to what we were trying to calculate here. And this is the formulas for the controller gain. And this assumes that you have the 2 time constants and a dead time and the plant gain. Then the integrator time constant is easy to calculate, and so is the derivative time constant. And this will result in a very well-tuned system. Give me a like. This is part 1 of 3. And the next one is going to be about getting doing the system identification on a real system. Bye.